In the bit stream, okay, any error in the bit stream, for example, this one might supposed to be 0. Okay, in the middle of the bit stream, 0 becomes 1, 1 becomes 0, lead to devastating errors. Okay, that means everything is out of whack. Okay, you're not synchronized anymore, and whatever the rest of the way will just there's no warranty that we can say. Okay, that's in the worst case scenario, we lose everything from here on. So we have to discard everything from here on. The solution for this type of problems is to insert resynchronization markers. Okay, so for example, you can have a start code that look like this. Okay, and whenever you see the start code, you restart the decoding process from 0, from the beginning. Okay. Now, one of those start codes might be maybe the beginning of frame codes. Okay. So at the beginning of the frames, we have a start code. Okay. This is the starting of a frame. And you can do the same thing with, this is the starting of a slice, or this is the starting of a group of microblocks. Okay? So these are synchronization markers that we put in the code so that here we can start decoding independently with respect to the previous bit. So that will eliminate some of the error bits, okay? Because if you make a mistake here, error happens to be only from here to here. Then you resynchronize, and everything will be okay. So this is in Huffman codes and also in the arithmetic codes that we studied before. We never consider robustness. We never consider the fact that the channel will have communications errors. Okay. But now we know that there's communications errors. Then the question is, can we design a code that might not be as optimal as arithmetic code, but at least provide some kind of protection? So for example, a very smart idea is called reversible codes. Okay? So for example, the way you do VLC decoding, you just start here. And you do table lookup for decoding whatever your decoding process is. Okay? And suppose that you decode all the way here and then, oops, I run into trouble. So this is a corrupted segment. This is where loss appears. Okay? Now, if you just use the regular Huffman codes or arithmetic codes, the rest might be history. Okay? You're done. Okay? Loss will come all the way over here. Okay? But then, if you have reversible code, what it means is, if you decode from the left, okay? You run here, run into arrows, you say, okay, fine. I'm going to start from the right, and then I go backward. Okay? So I can decode from the left as well as from the right. And that is called reversible VLC. Okay? This way, you can reduce, you can discard less data, okay? And suddenly it comes at a cost. Nothing really comes for free. Okay, it comes at a cost. The cost comes from the fact that you are willing to sacrifice some of the coding efficiency. Because if you just do it the optimal way, like arithmetic coding, it's not going to be reversible. Okay, or even when you do Huffman, it's not going to be reversible. So an example of the combination of reversible codes and synchronization codes will be like this. There's an error here. There's a synchronization markers here. So from here on, everything will be okay. There's a problem there. Okay. So you you run into a problem right here. So you look for the next marker. You look for the next synchronization markers. You know that's the end of the slice or whatever, and then you work yourself backward. Okay, you work yourself backward all the way, and maybe up here you're still okay up the way until this point. So then you only lost the one in red, and you can still recover the one in blue. Okay. Now an example would be a non-reversible code, okay, which is this one, and a reversible code, which is this one. Okay, so let's do a comparison. Okay, now in order to be a good code, we need to satisfy what conditions? Prefix conditions, right? Do we satisfy prefix condition here? Yes. We're okay with 0, 0. We're okay with 0, 1. We're okay with 1, 1, 0. We're okay with 1, 1. Looks like we satisfy the prefix condition. So this is a pretty reasonable code. Okay, at least it behaves very, very well, and it looks like it has variable length. So maybe we can show that this is not quite as often. It all depends on the probability of 0, the probability of 1, so on and so forth. Okay, but I'm pretty sure that if you design software code from the correct probability, you might perform better than this. Okay, but it's okay. This code has a probability, has a property that when you flip, okay, so take 0, 0, well, the flip is itself. When you take 0, 1, the flip is 1, 0. So that means you can do backward as well as forward, right? Backward as well as forward. Okay. Now when I reverse the code word, I still have uniquely decodable code. I still have uniquely decodable. Okay. So what is the properties of the code such that you can satisfy these conditions? I leave it to you to explore. But I just want to say that there exists code like this, okay, that actually can be pretty powerful in terms of error detection and corrections. Okay? So whenever you run into trouble going from left to right, you look for the next unitization markers and you work backward from right to left. Now, data partitioning or packetization is another technique that people use all the time to gain robustness in communication. So the bits closely following the resynchronization markers are more likely to be accurate than those farther away. Right? Can we say that? Because it doesn't have that propagation effect, right? Right? The farther you are away from resynchronization markers, you open yourself up to more errors, the type of the type of propagation type of error. Okay? So the idea is to place the most important information where? After near the resynchronization markers. So whenever for example, you have a marker block, which can be treated as a resyn marker, right? Maybe at the beginning of each marker block, we add a resyn marker. Okay? Then I will put the motion vectors here because it's very important. Then followed by less important data, like the residue. Okay? And then I have another resynchronization markers, another motion set of motion vectors here, then the residue, so on and so forth. Okay? So that's another technique that people use. Now, error propagation comes from the fact that you have P frame, which is predicted from I. I means you encode the frame as is. There's no motion. There's no motion estimation. Okay. So when you make an error here, okay, it has devastating effects because you look for motion. You do motion estimation from this frame based on this frame. Okay. And if you make an error, then you have this red block, okay, red circle, okay? Now, this P frame is going to be predicted from this one, okay? And the way we do motion estimations, blocks can be overlapped, right? Okay, because we search for windows and we might catch a red corner of some kind, okay? If you catch a red corners, for example, you catch this corner, then you introduce that errors. You introduce that errors, right? And then you go over here, you predict this one from that one, you catch another errors and it expands this way. And then you expand, if you catch this corner, it expands this way, you catch this corner, it expands this way. So it keep on expanding until an iframe comes. Until the next iframe comes. Right? The next iframe comes. Iframe is decoded, okay, is encoded by itself. So you decode it as is. It doesn't have any prediction across the frames. So then you resynchronize. And you're happy. Okay, if you watch digital television, you're going to see this a lot. Okay, there might be a plot that get lost. Okay, and then it would lead to a whole bunch of other plots nearby. And then after about a second or so, then everything is okay. Because the next iframe comes. The next iframe comes. Okay, that's your saving. Okay, your iframe is very, very nice, especially when your channel has a lot of errors. Okay, so that's the type of error we call error propagation. Okay, and as you can see, the P frame is already bad. Imagine you have B frames. B frame is bi-direction. Okay, so you predict it. For example, you predict this one from this and that. You know, that errors can come from a lot of places. Now, how do we limit error propagation? How do we limit error propagation?
Insert smaller iframes.
We insert more iframes. That's one thing to do. Very good. Okay. What if we cannot insert too